All right, hello everyone, and welcome to our third colloquium. We are being presented about the placenta paradigm by Minna, so please give her a warm round of applause. Okay, hi. This is going to be a talk about research I did last summer at Sick Kids in the Mice Imaging Center, which, as the title indicates, largely focuses on imaging pregnant mice and the resultant placentas. So during this summer, I did work with two PhD students in medical biophysics. One of these projects was very easy to explain, and was very successful, and the other is not so easy to explain, and it is not so successful. So we will be discussing both paradigms today. So the first thing I did with the graduate student Anastasia Smolina, whose research largely revolves around doing things of exactly this kind, was building a classifier. I'm going to explain what that is and why you should care. So the goal of this project is to build a classifier to identify stained placenta tissue, which means that we should be able to input histological images of a placenta and have the classifier give us back how large is it, what regions are dead, what regions are alive, what regions are feeding nutrients, and what regions are actually connected. So the approach is largely standardized in medical biophysics. We use existing QPath tools. QPath is just the best software for this, and by the best, I mean it barely works. And the process is to take over 200 samples, outline them as you would like the classifier to be able to identify them, annotate regions of interest, and then sort those annotations into this is placenta that we care about, this is something that's actually dead and not providing the fetus with nutrients, and this is actually just blank space in the image. Some challenges of this approach are that, like I said, the software is not the best, it's just the best we have so far, and the homogeneity of the images, I will go more into this when I show you the actual results, but the placenta tends to look largely the same, so it's difficult to figure out what is important to look at and what isn't, even for a person who's looking at it. The results of this, which are theoretical here but became practical in life, a classifier that can, based on new images and new data, outline the placenta in histological images and give an estimate of the tissue area. Ideally, it would give an estimate of different parts of the placenta and how large they were and how effective they were at doing their jobs, but we didn't get there over this summer. And that has to do with the next steps, which were improving the accuracy of the classifier with further annotations and distinguishing different parts, such as the junctional zone, which is an area of the placenta you might not be familiar with. So, like I said, the project is to build a classifier that can identify stained placenta tissue in an image. And the broader aims of this are to use said area estimations to help determine how placental insufficiency affects the developing fetus. In the 2016 Amsterdam census, they came up with a number of ways that insufficiency of the placenta can affect development of the fetus. One of the important applications of this from mice to people is that mice mature at a much faster rate, are much easier to test on, and we are largely able to take findings that we have in mice and extrapolate them to people to help with certain birth defects and so on. So what is the placenta actually? It is an organ that supplies the fetus with oxygen and nutrients, and insufficiency or underdevelopment or damage, depending on what you do to the pregnant mouse or individual, can be damaging to the fetus and lead to issues down the line. So it's interesting to examine how insufficiency actually affects the fetus, and in order to do that, you have to have an idea of what the standard should be, what the general size should be, what it should look like without any perfusions or mistreatment, and then extrapolate that to what happens to said fetus. But that's actually largely not what I worked on, so we will be exclusively discussing step one, which is very much informed by machine learning. And so the image I have included here are of some chihuahuas and some muffins. If you would like to do the first step of machine learning yourself, you may figure out which one of these are dogs and which are muffins. It's a fun exercise. It's harder than you'd think. So what is the idea of machine learning? Well, largely it's to make jobs like the one I did last summer irrelevant. Like that you have a machine that can tell you this is the size of the placenta, this is a dog, this is a muffin, and have it actually be correct, which is the idea of increasing robustness. And so the specific part that I was working on was not designing the actual algorithm for this, but training data with labels and then testing what you want to segment and what you want to look at. Basically what you do is you take a bunch of images and you say, here's positive, here's negative, here's ignore, and you give the machine a lot of examples of this. And then it's actually only valid if it works on images you haven't shown it before, so you have to decide which data you're going to train it on and which data you're going to test it on. And we only care about how useful it is in new situations. If it can correctly re-identify the annotations you already gave it, it's actually not useful. It's just reiterating your work. I hope that makes sense as a concept. So I can move this. This is an image of a mouse placenta. This is a really cool image. This is in QPath. What is actually super interesting about this is that the image of this that this is taken from is the size of my nail. And you can blow it up to this resolution and essentially lose nothing. You can look at this and have a perfect idea of exactly how it looks in this tiny, tiny slide. The PhD student I worked with this summer, she had all the images I was working on, or well, all the slides with the, I guess technically you cut off a little bit of the mouse placenta to take this image. This is not an ethics talk. And she had like 300 of these slides just in her drawer, and she would pull them out and be like, do you want to see these? And they're really cool. And it's even cooler to see how large it actually is and then blow it up to this size. So the approach of this project is that you take 200 or so images of these. They're stained with, I actually can't remember what this stain is called, but, oh, it's PAS stained tissue. It's called periodic acid shift, and it identifies glycogen. Perfect. And then you spend an enormous number of hours annotating what your regions of interest are and classifying them into the sections that you want the computer to be able to identify. So the most important things to look at when you're doing this are, where are the soap bubbles, where are the issues that the computer might not necessarily be able to detect, because it's fairly easy to get an idea of like what is dark purple. It's less easy to get an idea of, oh, this part is actually dead. There are no nutrients transferred here because this is all dead tissue. It's also harder to get an idea of like where this is a soap bubble and this is also a soap bubble. So these are the ones that you want to largely like tell it to ignore or leave out. And then the issue I talked about earlier, which is that it looks largely homogeneous, is that if you actually like zoom in very closely on this, you can see that there are some things which are dead that the computer is classifying as area that you then have to be very precise to not see as area. The easiest way I can think of to explain this, especially to the demographic here, is that this image is actually a matrix. And in every, like, I guess, tiny, tiny cell, it's like 0, 1, or 2. And then 0 is there's nothing here. 1 is there's something here, but we want to ignore it. And then 2 is like, this is the area we actually want classified. Yes? Oh, it's a, like you take the microscope and you take a picture, essentially. That's what that is. Right. I sometimes forget what the original context of this is. Okay. So this is an example of the kind of pixel classifier you can make with QPath. These are some, I guess, specifications that will not make any sense to you, but based on how you vary these, they can make slight differences. Again, some of the challenges of this project are that the images kind of all look the same, and if you haven't seen a lot of images of mouse placenta yourself, it's difficult to figure out what to label. And incidentally, that's like what the benefit of having the classifier to do it for you is. It's so you don't have to sit down for like 4 weeks and outline all these images of mouse placenta. And some of the limitations of doing this are that the QPath framework is extremely memory intensive and extremely slow. So you can be, like here, you can be zoomed in on, this show, you can be zoomed in on like this tiny area, and because that uses so much memory, because this is being blown up so big and you have to go in so closely, like the computer would like shut down every 30 seconds. Not every 30 seconds, that's an exaggeration, but it would frequently, the amount of memory that this requires to run would make the computer shut down. So you have to hit save as often as possible. So what happens when you actually do get a nice classifier that tells you what's up? You get pretty ones. So there are various versions of the one that I made. This is the one that had the most data. This is the one that I think has like 120 images that it's classifying based on. So if you look closely, you can see that the red tells you what the area is, and then these like white and purple spots are stuff that it is actually not correctly picking up, and then the blue is the background or the stuff that we're ignoring. So based on the classifier, random trees, like when you select that option, it looks a little bit better, like the edges are neater than the artificial neural network because that's not actually trained on similar data. Moderate resolution gives you results which are somewhat fuzzy, but higher resolution is so memory intensive that it's hard to run for as long as ideally you would want it to. Because the idea is you want to like feed as much data as possible into this so you get the best idea of what your images are telling you. And this is an example with more moderate resolution. And I should also mention that these are examples of how the classifier works on new data. So it wasn't trained on this. These are images that were not annotated, and this is its guess of how large it is, for example. The other benefit of this project was that now you had like a human who went through all of these images and said how large they are, so it was actually a much higher degree of accuracy than the classifier ended up being. Yay! So this is a very close image. Again, this is a tiny, tiny fraction of an image that is smaller than my nail. This is incredibly cool. So the red is telling you what the classifier thinks is the area of the placenta. The purple is the original image showing through. And the white is, like I said before, the background. So there's like a little table you can make of like what the results for this look like. It's like through. I have no idea what kind. I think this is a truth table, but I'm not 100% sure. So the red is showing you like what's a true positive and what's actually area of the placenta that we care about. True negative is the white, the area that we would like to ignore. The false positive is when the classifier accidentally picks up the background, which didn't really happen, but that's the false positive. And then the false negative is, oh shoot, did I confuse myself? Yeah, the false negative is when it tells you that something isn't connected, but it actually is. So, that's not so easy to denote. But that's kind of the idea of how you assess how correct this is, how well it is performing. And here are some next steps that could be taken in this project that are, because ideally when you do medical biophysics research, you want to have a large variety of these classifiers for a large variety of images. Me looking at the specific selection of images of the mouse placenta is a tiny fraction of the work that actually goes into creating a PhD thesis. So step one is to improve the accuracy of the classifier, label images which are more distinct from each other so that it can be properly trained in a large amount of data. And then test the generalizability of the classifier in brand new images, i.e. not ones that were taken by Anastasia Smolina in her lab, but ones that were taken in a completely different lab that's using completely different technology, and see whether it can still correctly tell you what is placenta, what is not, how large is it. You can also expand the number of classes. What I ended up doing was saying, is this a placenta or is it not? Is this connected or is it not? But you can generate more specific annotations to outline particular regions of the placenta, like that do different things, that send different nutrients to the fetus. And then you can, and this is the actually useful application of the research, that's not just like playing around with images. You measure placenta sizes in pregnant mice that have been treated well and treated poorly, and see how the size of the placenta corresponds to the health of the fetus after it's born, which is the overarching like top level goal of the project. So this was very successful in the end. I will now be switching to something that was slightly less successful, and it was actually done in MATLAB, and it was to simulate blood flow in the umbilical artery which connects the placenta to the fetus. You will be having a grand old time with this, as I did. So the overview of this project was that we wanted to determine possible reasons for blood velocity underestimation in ultrafast Doppler measurements compared to conventional techniques, which is a very long sentence, I know. However, basically, when they were traditionally looking at how fast blood moves, they came up with a certain number, which I don't remember, certain number, and they said this is how fast it's supposed to move. Versus when they switched to ultrafast Doppler imaging, it was the how fast the blood was moving. Like the estimation they were getting was wasn't wrong. It did not align with the traditional method. So the goal of this project was, if you code it, essentially you remove human error, and you try to figure out in the like MATLAB space what's going wrong. Maybe you can extrapolate that to how well it works in the real space. And so you create MATLAB code which simulates how like this one red blood cell, all of this code that I will be presenting to you is based on like looking at one cell, and applied Doppler measurement techniques. I use with large air quotes. There were no images involved in the generation of this code to determine how fast it's moving. Challenges in this project were limitations of MATLAB's MUST package. Actually, the #1 issue in medical biophysics is that absolutely nothing works. The other issue, which is really funny, and I will come back to it a lot, is that eventually this started predicting that blood moves at the speed of light, which was like wildly obviously incorrect. And also that the data would just generate graphs. Because we invented this data, this is not real data, it just generated graphs that look wrong. So essentially this progress yielded, let's go with almost absolutely nothing, but the approach is still interesting to discuss. So here's an image of like an actual mouse placenta, as opposed to the earlier image of the placenta. So the project is to simulate the movement and like image, again, this is not real. We have invented this red blood cell and all of this data is fake. A red blood cell in the umbilical artery. And then based on having imaged that red blood cell, you come up with some hypotheses for why the ultrafast Doppler imaging is underestimating how fast it's moving compared to the traditional technique. And it is okay if a lot of that like jargon is going over your head. I will go into it. But speaking of the first project, this is where the junctional zone is. Yay, it's all connected. So this is MUST. This is the MATLAB ultrasound toolbox, which allows you to invent all this funny data. It contains tools that are useful for simulating it, but also like processing actual ultrasound data. So it works both ways. So using MATLAB, I coded this simulation. I made up some data sets. So there was one with multiple red blood cells that for some reason we thought would work better, but every result is like based on this one red blood cell because that didn't work. And so then we kind of went through, if I were actually imaging this red blood cell, what would I do to determine how fast it's going? So we did some beamforming and we did some Doppler processing, and all of this will be explained in detail. But first we will talk about the challenges of this approach and why it doesn't work. Basically, when you look at how fast red blood cells are moving, what you're doing is you have a camera and you're taking pictures as fast as you can. So the MUST package gives you kind of a function to do this that's essentially like if I had a traditional camera and I could snap like 1,000 pictures a second. So it's not a good approximation for how it really works because the proportion is just so wildly off. And so this requires a lot of RAM, similarly to the project that I was working on in tandem with this. So basically both these very memory intensive like research projects end up crashing the computer a lot. We got graphs that don't make sense as compared to what you would expect if you were really doing this or doing like a successful simulation of it. And also, again, red blood cells traditionally move slower than light, so something was very off at that stage in the process. I fixed it, but I don't know why it ended up turning out like that, which is, I think, an important conclusion about physics research. Sometimes you get answers that like don't make sense and you don't know why, and then you're like, oh, but like I deleted 2 lines of code and that works. So the idea is that you have an artery, and then the cell moves on some diagonal path that I will delineate like this. And then you kind of want to take this verbal process and put it into MATLAB. Like it's almost like you're translating it. And so the first thing you do is you want to code transducer parameters. A transducer in medical imaging is a device that produces sound waves which bounce off body tissues and make echoes, based on which you can tell how far away it is, i.e., how much it's moving. And then, so we had some transducers that we were doing when we were taking actual data in the lab. Not that I ever went into the lab aside from one very fun time. And so there were some of the actual transducer parameters that we used and some of Must's like default. And the reason that this became an issue is because, again, Must's default is a camera that can take 1,000 pictures a second, whereas we had a camera that could kind of take 60 pictures a second. So it wasn't like a one-to-one. I guess it wasn't a one-to-one simulation. It didn't accurately depict what we were interested in depicting. Then we did something which is called beamforming in medical imaging, and it's basically you have some volume of interest, which is the volume of this artery, for example, and then you take how the pressure is distributed and what the amplitudes of the pressure are, and then in ultrasound you recombine those signals to generate images. And that is, I guess, like the example of how beamforming works that doesn't require you to know anything about medical imaging. After this was done, we did some Doppler processing, which I think everybody learns about the Doppler effect in high school, and it's essentially that you use the sound waves in the Doppler effect to reconstruct where the red blood cell is at, like, let's say this is T1 and this is T2, and that's Doppler processing. And that was the part that was going wrong experimentally. This was giving you an underestimation compared to what you would expect. And then the last step of this was the Fourier transform to look at the power spectrum. And the Fourier transform is an integral transform that takes a function as input and gives you a different function that describes the extent to which various frequencies are present in the original function. And then the output is a function of frequencies. So you go from function of time to function of frequency. And that is not like a holistic example of how Fourier transforms work in math. That is an example of how Fourier transforms work in medical biophysics. So this kind of works. This position time graph of the red blood cell is like, what if I had one red blood cell and it just went from one side to another, which is just like this. And then the second image is like, what if I had multiple red blood cells that were all going like this? And I know I said that all of this would be based on the movement of one red blood cell, but I actually lied because I forgot that this was something that actually worked for the blood cell. And then here is what happens when you try to reconstruct that image via beamforming, which is a signal processing technique that we reconstructed from a signal that's based on, I guess, to extend my camera analogy, the cameras you're using and the area in which you're taking them in. So you apply like a time delay to determine where those signals came from in the artery and form an image to tell you the positions. And you might notice that this like doesn't look like it's a transformed graph of the graphs that were on the previous slide. Well, the one on the left actually kind of does look correct based on it coming from experimental data. And then the result from multiple scatterers is, well, this is wrong. This is not how you would expect it to look. It should look more like dots. Like if you were ideally doing this, it kind of looks like a parabola. But it's connected for reasons that were beyond me, the PhD student, and the supervisor. This is just fun. So this is the Fourier spectrum. This is frequency versus power. You may notice that that is just a straight line, and you would be correct. This is, again, not a Fourier spectrum that you would expect from the image. And that's like the equation that you use to figure out what's going on here. This is the Doppler effect. One thing that is actually like to note about the slide is that Must's package was updated on June 16th. And before that, like this looked different. Like this had peaks for frequency and everything. But because I was unable to reconstruct it with the new version of MUS, I could not correctly explain how it had gone the first time. Hence, we have this frequency that, as I said, doesn't really work. I don't know why. Yeah, this is another attempt at reconstructing the Fourier spectrum that was perhaps more effective. We expected to see a peak at the frequency that corresponds to the velocity of the blood cells. So one advantage of this simulation as compared to the actual process is I was supposed to know how fast these were going. Like that was supposed to be a parameter I set, which I hate to keep coming back to this, but that is like the funniest thing about the fact that it ended up returning the velocity as the speed of light. Like I said that. I said v equals such and such, and it was not, yeah. Anyway, so our spectrum, this spectrum does not look like what you would expect if you were constructing a Fourier spectrum. It looks more like noise. And so the initial assumption for why this doesn't work is that the signal from one scatterer wasn't strong enough, image from one camera. However, no. However, when you tried to do this with multiple scatterers, all the matrices that you were trying to input into MATLAB's functions in the end up overwriting each other, so you cannot get an image at all. Must is actually not the ideal software to use for this, for some strange reason. Anyway, so these are some next steps, which are essentially that this process doesn't work and we need to find out a different way to do it, which sometimes happens in the lab. You make a guess and it doesn't work well. So modifying the parameters of the simulation, it was something I did and that largely didn't work. However, there may be some kind of a construct where I guess you don't initially define how fast this is going or where it is, and you just kind of rely on the program to pick it out. That could tell you what was going on. Because the velocity that I set at the beginning and the velocity I got back at the end of the processing were never the same number, which doesn't really tell us anything about how it worked experimentally, but does tell us that the simulation was not an effective way to look at it. So basically the best idea for how you could continue with the problem, and I think this is what the PhD student whose thesis this is doing now. Her name is Jessica Peng, and she's a lovely person. So is that you could define the scatterer with a different program and then analyze the data set with MUST instead of using MATLAB for this entire thing. You could also construct the simulation in Python, which has like better support for ultrasound imaging simulations. That is what she was doing, and it was actually largely more effective than this. So in conclusion, thank you for listening. And if there are any questions. Mm-hmm. Well, the thing is that in the lab, you look at like a very specific case of a very specific thing because that's the easiest lens to look at research on. The broader implication of this is that you can use it to analyze relationships between the size and function of the placenta and how it affects the fetus, which is kind of the research that's done for like conditions that develop in infancy and how that affects the child as they grow up. So that's what the application is. It's largely medical. Yes. In this graph, this is an extension of like how the pattern was supposed to look that has no physical meaning, but was supposed to explain to us where the peak should have been. Not like if you look at where this peak is, it's essentially at 0. And as stated, like that was not the speed that it was supposed to be moving at. Yes, Daniel. It's a medical imaging process. So you have like, I'm not gonna explain this very well because I didn't actually work with this equipment. I just pretended that I had the equipment and was correctly using it. You fire a sound wave at this, and then it comes back, and then based on the delay between when you send the sound and when you get the signal back, you can like guess how far away it is with relative accuracy, unlike the simulation, which has no accuracy. Yes. What was the last part of the question? That's a good question. I know that one of the other professors that I had emailed about this kind of medical uh, medical imaging research does images of the human heart of very small babies and how like those function and how those work and how you can guess like how well it's working and how well continue to work over time. I don't know much about the methods that his lab uses, largely because I read the papers a year ago and I can't remember them anymore. But the I guess the reason I thought talk would be somewhat useful is because the idea of using machine learning to identify what's happening in images and then using simulations to identify what's going wrong in your lab are largely like the bread and butter of biophysics research in more complicated contexts than this. Yeah, they do a lot with this. Yes. Yes. Thank you for the talk. Could you go back to the slide? Indeed, I can. Where's the? Yes, this one. Yeah. So the first one. Yeah, sure. Okay. So that's a good question because I was so proud of the camera analogy and it hasn't worked ever. So if I have like, I guess let's look at this piece of chalk and wanted to photograph it as it's moving through the air. Like imagine that it's moving of its own accord. I take a picture of it, take a picture here, and then I take another picture like a second later and it will have moved some distance, and then take a third picture over here. And based on the distance it moves in those between those images, I should be able to do some processing to get an estimation of how fast it's going. So that's the idea of the camera analogy, that I'm taking pictures of something that's moving and using like the displacement in each of the images to calculate the velocity. Does that make more sense? It's okay if it still doesn't. It's a safe space. Then what did you mean by that? Yeah. So when you actually kind of use this strategy when you're like looking through a microscope or whatever it happens to be, when you're actually imaging the artery itself, you have a machine that can take 60 pictures in, I don't know if it's, I guess second is an arbitrary demarcation, but let's say it can take 60 pictures in a second, and then you have 60 data points to work with. So the way that the camera in the MATLAB simulation works is you can take 1,000 pictures. And so whereas in the lab you're getting pictures that look like this, on the computer you get images that look like this that don't actually reflect how much data you would be able to get, and hence don't give you a good idea of what's going on experimentally. Yes, Joel. I had a couple of questions. Oh yeah, for the classifier, what was the architecture of that? So that's a good question that I don't really know the answer to, because I guess QPath is not so much like a machine learning software as it is kind of a Photoshop software. Like you can look at the images and you can encode parameters, but it doesn't give you a big idea of how those parameters are actually being used to classify the image. So the answer is that the name random trees, which is based on an actual machine learning principle, which I have forgotten and at one point could explain to you, but at this point cannot. These are parameters that you're allowed to use to decide what the classifier is looking at. I do not actually remember what the architecture behind them is. Yeah, so the results of my classifier, this is, like I said, a widely used paradigm. You expect that the area estimation can occur with like 80 to 90% accuracy. I was clocking in around 85. So it was average. It was nothing special, the thing I came up with doing here, but it was roughly what you would expect in the field. Yes. So like, analyze like histology Mm-hmm. Yeah. No. That's a good question. You can compare these histological images with, like, let's say MRI images. You can compare them with images that were obtained with X-ray. It depends on what you want to look at. The MRI is really cool, but it's also really powerful, and often for very small things, it doesn't give you a good idea of what it actually looks like. So when you're like, the overarching aim of this project was to do size estimation, and that's what this type of image is best for. So you can compare, but it is based on like what material data you want to extract from what you're looking at. I hope that answers your question.
Question
Yes.
about,
Mm-hmm.
so I guess you said that you assumed that the blood cell might
Yes.
how good of an assumption is that?
It's a terrible assumption. Yeah, it's a terrible assumption. It does not work. Sorry, the conclusion of that project is that it doesn't work. But when you actually have a blood cell moving in the artery, it again like has all of these collisions that, like you rightly pointed out, occur on its path and that deter it, and like as it contracts and expands also change the way it's going. So I guess the idea of the diagonal path was largely to see whether we could get a decent velocity estimation, because it was kind of like, here's a perfect principle, here's a perfect red blood cell, can you get anything meaningful out of this simulation? And the answer was no.
Would you say that that's the reason why?
That is the kind of the $1,000,000 question of the research. If I had to guess, I would say that because of the contraction, expansion, and like various things that are happening, the Doppler ends up being, because the Doppler relies on sound waves and the traditional imaging methods rely on pictures, as I kind of explained in the camera example. I would say that that the diversions in the path are what's causing the issue. But again, like I feel like that's a guess that I would be able to better defend if I had access to lab equipment. I was very sad about not getting to use the MRI. I kept asking. Of course. Joel. Yeah, like they were on like little glass slides that they basically shave off the top layer of the placenta and like flatten it, image it, and then scan it into the computer. Hey, that's a good question. I think that it would. I think it would change volume estimations. I think could be hugely helpful in what is trying to be accomplished with this project. But it's already so small that I can't see how it would make a difference in estimations. It would make annotating them a lot harder, though. A lot more annoying. Any other questions? You can come harass me in the lounge if you want.
That's it.
Thank you.